All right, so let's talk about section 1.2, which is now going to transition us from the system form to matrix form. All right, so without further ado, let's define formally what a matrix is. A n by m matrix is a rectangular row with n rows and m columns. All right, so just keep that. That's the big thing to remember here is that the first number is the rows, the second is the number of columns. Right, so for instance, here we write with brackets entries, just like that. There are 2 rows and there are 3 columns, so it's a 2 by 3 matrix, plain and simple. When we're talking about generic matrices, like n by n matrices, and we don't want to actually give numbers to the n and the m, and we want to refer to a very particular entry, we'll call a sub ij the entry where the row is I and the column is j. Right, so here, for instance, we have a1, 1 is 3, a1, 2 is -1, so on and so forth. Right, so just remember that the first subscript is the row, second one is the column, and it's the same order in which the n and the m are in the size of the matrix. All right, so for instance, the reason it's nice is we don't really care the names of the variables when solving systems. We just care about what's happening to the coefficients and eventually what the values of the variables are in the very end. So we don't have to keep writing them out every time, right? So all we're going to do here is we're going to strip off the coefficients, right? So there's a -1 here. And we're just going to plop them into a coefficient matrix, right? If we want to have the whole system in a matrix form, then we're going to keep on the left side the coefficients, and on the right side, we're going to put those numbers. Okay. The thing to keep in mind, there are a couple of bookkeeping things. One, a system has to be in proper form to do this. And so in other words, what I mean is on the left side, every variable can occur at most once. You don't want to have 3x plus 2x minus y here and then plug the 2 and the 3 into the matrix, right? So there you have to simplify the equations first, and the only constant terms can be on the right, right? That's the critical thing. Number two, the variables have to be in the same order in all the equations, right? So again, that'll affect the matrix if you don't have them in the same order. You don't want to have 3x minus 5 is 5 here, 7y plus 4x equals -2 there, but then identify the entries in the matrix in the same order they appear in that system, right? So just be careful with lining things up. So let's look at just an example. Whoops. Just reduce this a little bit, pull it down. All right. Let's look at an example where we're going to write this in matrix form, and we're going to go through the exact same processes to whittle this down to that triangular form, the step-like form, echelon form, if you will, to use back substitution, right? But we're going to do everything in matrices. And it's kind of actually, come to think of it, let's go back just so you remember. Remember in that very first lecture, on lecture 0, that last exercise where I gave you a system and I showed side by side what the augmented matrix would be. So for example, here, we're not going to linger on this, just I want to show you, right? So this is the example I'm talking about. Here, now that we know what a matrix is and what a augmented matrix is, right? So there's this invisible line here that you could draw in. I typically do it just so I remember what the right side is, just for my own sake. But if you plucked the coefficients off here carefully, you would get these augmented matrices. And all we're doing in going from one to the next is performing those so-called row operations, one of those 3 operations allowable. All right, so that's what we're going to do here. We've already seen it in action once. Hopefully you attempted that before, but even if not, it's okay. Let's actually go through this one. Notice that we have every variable occurring at most once. The variables in the same order on the left-hand side, and then all the constants are on the right. And so I can immediately write down the augmented matrix, right? There's no x2 here, right? So there will be a 0 in that spot. But for the first row, we get a 2, a 2, and a 1, line 4. And then over here, we have a 1, a 0, a -3, and a -2. Remember, the 0 is because there is no x2. You need that placeholder in the matrix. And then 3, 1, -2, and 5. All right. That is your beginning system. And what I want to do, I want to write this in echelon form. Echelon form, remember, means that every line has fewer variables than the previous one. What that would mean is that in the matrix, you're going to have more initial zeros in a row than in the previous row. Strictly more. It can't be just equal to, it has to be strictly more zeros in a row as compared to the previous one. And so what I'm going to do here, the first thing I'm going to do, and this is just for a matter of preference, if at the very end, at the very last equation you have here, that's the one that requires the most work to find the value of the variable corresponding to that entry. So the less algebra I have to do, the better. And so it's preferable to have a 1 in this position, so I don't have to eventually divide, right? So it's kind of motivated by laziness in some sense. But what I'm going to do, since I already have a row with a 1 there, I'm just going to interchange rows 1 and 2, right? So the notation I use there is R is for the row, the subscript is the number of the row, and this double arrow just means I'm going to swap them, right? Double arrow means swap. And so, and remember, I'm allowed to change the order of 2 rows. That was one of our elementary row operations, right? So I did nothing algebraic. I just interchanged the order in which they were written. That's fine. Okay, so the next thing is I want zeros in both of these initial spots, right? Because any row beneath this guy has to have more zeros initially. So both of these rows are going to have zeros there. So to that end, I'm going to first multiply the first equation by 2, -2 rather, and I'm going to add it to that second equation, right? Remember, I don't have to have the variables there. They're there in behind the scenes. I'm just going to multiply this row by -2 and add it to that one. That corresponds to adding -2 times the first equation to the second equation, and I'm going to replace the second equation by that result, right? So the notation is multiply the first row by -2, add it to the existing row 2, and plug that in then for row 2. Okay. If I do that, you could check the arithmetic on this. I'll get 0, 2, 7, 8, and I didn't do anything to the first or the last rows. Okay. Now I'm going to do the exact same thing here. I want a 0 on this initial spot, and so I'm going to multiply the first row by -3. I'm going to add it to the third row, and I'm going to replace this third row by that. That's what this arrow means. Take this and replace this row by it. Right? So again, if I do that, I haven't changed the first 2 rows in so doing, but I am going to change this one. Right? If I multiply the first row by -3 and then add component-wise down, what I will get is 0, 1, 7, 11. You can check that out. Okay, next thing, this is not an echelon form yet, because while this row behaves correctly with respect to the one directly above it, this one does not. This one has it doesn't have fewer zeros than the row directly above it, and so I need to make this guy a 0. Well, how do I do that? Well, I'm going to take 1/2 of the second row, right? And I'm going to add it, pardon me, to the third row. -1/2 part. -1/2 times R2, that gives me a -1, and I'm going to add it to R3, and I'm going to replace R3 by it. All right, so I get a 1, 0, -3. I'm not changing the second row. The third row now is going to become 0, 0, 7/2, 7. Okay, this is an echelon form. Right, every row has more zeros initially than the one directly above it. Notice also it's in that form where we can now immediately use back substitution, right? So now is the time where I'm going to change this back to system form, right? So we didn't have to write all those crazy variables each time around. It takes too much time. Now we have this nice set of numbers that corresponds to the coefficients and right side of an equivalent system. So what do I get? This is the same as x1 plus 0x2 minus 3x3 is minus 2. Right, so these are the coefficients of x1, x2, and x3 respectively. Then I have a 2x2 plus 7x3 is 8, and a 7/2 x3 is 7. And now I'm going to use back substitution to solve. Right, so you start down here, x3 is equal to 7 times 2/7. Bong, out they go. I get 2. Plug the 2 back in here for x3, right? So I have 2x2 plus 7 times 2 equals 8. Right, so I know this. That's 14. Subtract that from both sides, get minus 6. Divide by 2 to get minus 3. And then I'm going to plug these guys both in here to get x1. Right? X1, there is no x2. Minus 3 times 2 is minus 2. That's minus 6. Add 6 to both sides to get x1 is 4. And so notice we have a unique solution. Write them in the order of increasing subscript. So it's 4. X2 is minus 3 and x3 is 2. This is the unique solution. All right. So remember the convention here is if you're using subscripted variables, you list the order in terms of increasing subscript, right? Otherwise, if it were X, Y, and Z, you really have to tell the order because there's no way to think why somebody wouldn't want Z, Y, X, right? It's not usual to do that, but it's still plausible that someone can do that. All right, so just keep that in mind. All right, so just a reminder, echelon form, keep harping on this, but echelon form is any so if I were to have had 0 rows, which I don't, but if I have any 0 rows, all zeros across the board, they go at the very bottom, right? So they can't have any more variables than the ones above them because they're all 0, right? So there could be multiple of these guys. All the 0 rows go toward the bottom. And then every other row has more initial zeros than the one before it. Okay, so that's echelon form. That said, echelon form is not unique, right? I could have multiplied this row by 1/2 and replaced this row by that 1. So in other words, if I divide everything by 2, I could have had 0, 1, 7/2, 4 there, and that's echelon form, right? Completely equivalent to that system, but the form, the echelon form is different, right? So this is not unique. It just, the conditions are that the 0 rows are at the bottom and that each row has more initial zeros than the one prior to it. That's the only condition on that. All right. Okie doke. So now let's actually just go through here and see if these these matrices are in echelon form according to our definition. All right, so notice here there are 2 rows, right? This row here has more initial zeros than the one above, right? There are no 0 rows, so that's an echelon form, yes. Plain and simple. Just in terms of terminology, we call the first non-zero entry, if such exists, a leading term. They are also called pivots, so it's the same term. So leading term means the same thing as a pivot. I suspect pivot has a more interesting, there's a good reason why pivot is used versus leading term. We'll see that later. This one here, is this an echelon form? Well, there are no 0 rows, so we don't have to worry about that condition. And row 2 has more initial zeros than row 1, so we're good. But this row does not have strictly more zeros than the one above, right? So this is, in the definition, this more means strictly more. It's important. Right, you could have done more to put this into echelon form. So this one is the reason for it not being an echelon form. Okay, not bad. All right, let's go through and solve the following system. Whoops. Eventually, by the end, maybe I'll get this zooming nonsense right. All right. There you go. Now you can see. Excellent. All right, so let's actually go through again and go through all the same steps to get this down to an echelon form so we can solve the system using matrix methods. Again, just to make sure, I'm not going to try to trick you with this, but in practice, when you're forming the matrices in an application or whatnot, it's very easy to just forget to write the variables in the same order, and then it can just slip your mind when forming the matrix. But just check all the variables exist or just once in every equation, so that it's not necessary to simplify further. They're all in the same order, and there are only constants on the right-hand side and no constants sprinkled on the left. All right, so all those conditions are satisfied. That said, we can form our augmented matrix, right? It's going to have 4 rows. The rows are the number of equations. It's going to have 5 columns on the coefficient side because there are 5 variables all told. And then it'll have a 6th column because we're going to form the augmented matrix. Okay, so let's do this. We have a 1 and a 1. There's no x3, x4, x5, so 0, 0, 0, line 6. Right, so I'm just going to put up here just to remind you. This serves no purpose aside from a reminder that that's what these represent. Okay. The next one, we have a 1, 0, 1, a negative 1, 0. Don't forget the negatives, right? So that is part of the coefficient that goes into the matrix. And 3. Then there's no x1, 0. x2 is 1, x3 is negative 1, no x4, negative 1 for x5, and a negative 4. And then now the first 3 variables here are 0, 1, 2, 3, and then 1, 1, and 7. Right, so there is your augmented matrix. Okay. Well, what I would like to do, remember, is get the number of zeros in every successive row to be more than the one previous. And so the easy way to do that here, we have a 1 initially, so you can't get any more left than that. There are no zeros in front. But what I can do is interchange rows 1 and 2. Let's do that. All right, so I can interchange, I'm sorry, rows 3 and 4. I'll get eventually. 2 and 3. These 2 rows, because there's a 0 there. So let's do that. Leave the first row alone. 1, 1, 0, 0, 0, 6. Replace 0, 1, negative 1, 0, negative 1, negative 4. That's row 3 is now row 2. Row 2, 1, 0, 1, negative 1, 0, 3. That's now row 3. And then 0, 0, 0, 1, 1, 7. That is row 4. I didn't change that. All right. Now what I would like to do is get rid of the 1 here, right? So what I'm going to do is just subtract row 1 from row 3 and substitute that into row 3. Right? That'll get rid of that first. Oh, wait a minute. Or will it? Okay, we'll do that first. All right, so you'll see what I was hesitating about. So row 3 minus R1 into R3. What does that do? Well, you keep the first 2 rows as they are. Now, if I subtract R1 from R3, I get 0, negative 1, 1, negative 1, 0, negative 3. Right, so just subtracting R1 from R3 and keep that last row. All right, so now you see my hesitance. I had foolishly assumed that I would be able to keep that 0 there. But remember, you have to subtract every component entry-wise. And so I happened to get rid of the 0, but I gained 1 there. No problem. What I can now do is I can add R2 to R3 and replace R3 by that. Okay, so I'm going to keep the first row. I'm going to keep the second row because it's fine. If I add R2 and R3, I get 0, 0, 0, negative 1, negative 1, -7. And then the last row, 0, 0, 0, 1, 1, 7. Okay. Well, now we still not in echelon form because we have these two rows having the same number of initial zeros. So I need to replace the last row by one with more initial zeros. So what I'll do is I'll add R3 to R4 and replace R4 by that. Okay, keep the first three rows actually the same. Bong, 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 -1, -1, -7. And then if I add those two rows, notice what I get. Everything becomes a 0. All right, so you have a row of zeros here. This is in echelon form. Any 0 rows at the bottom, and for otherwise, all the rows have more successive or initial zeros than the one prior. So this now is in echelon form. Okie doke. So now let's actually identify what the pivots are right in here. So the pivots are the leading terms. So I got that guy, and this guy. Everything else now we have to determine the free variables. So that is free, right? So let's actually, I will convert this, well, let's see. That variable is x5. So let's let x5 be a free variable. That's free. But up here, we know that x4 is not free because it's determined there, but x3 is also 3, right? So I've taken care of that guy. This is not free. That is not free. That's free. This guy has to be free. All right, so you always start from the bottom row, identify free variables, and then use everything that you know into the next row up. Anything that is not known and is not the leading term is, again, a free variable. That's what I was doing. So in order now, what I will do, oh, wait a minute, this one's not free because we've determined that. I'm sorry about that. Right, so this guy was determined, this guy was determined, that guy was determined. This one is now known, so then all 4 of these variables are known in that last equation. So there are only 2 free variables, x3 and x5. All right, so let's go from here, knowing that this equation corresponding to this row is -x4 minus x5 is -7. Let's put in the x5 as s2. In fact, I'm going to multiply both sides by -1 first. So x4 plus x5 is 7. I'll plug in the s2 for x5 and subtract. So x4 is 7 minus s2. All right, so I have those. Going up to the next guy, we have an x2 minus x3 minus x5 is -4. I know what x5 is, that's s2. I know what x3 is, that's s1, right? So x2 minus s1 minus s2 is -4. And so x2 is equal to s1, adding those to the right, plus s2 minus 4. I also know x3. Okay. And then up here, I'm going to go backwards and plug everything I know in there. That is, I'm going to go up. I guess I can go here. Here, an x1 plus x2 is equal to 6. I don't know what x1 is, but I do know what x2 is. And then I'm going to subtract all that from the other side. So I get 10 minus s1 minus s2. There's your x1. And so now I can write my ordered triples. I'll go back up here. The solution is the set of all ordered triples with first component given by x1, then this guy in s2, s1, whoops, 7 minus s2, and s2, just plugging in x1 through x5. And I'm allowing both S1 and S2 to vary through the real line. Okay, so that is your solution set. Okay, so now there's something further than echelon form, right? So this is something called reduced echelon form. And what it means is that we have another condition, right? So each pivot is 1. So we have that clapped on. So up here, these green guys were pivots. This one's not 1, it's -1. So I'd have to do something further to that to get it to satisfy this other condition. All right. But not only that, the pivot can be the only non-zero entry in a column. So here we're good with that. If I multiplied this by -1 to get rid of that negative sign, this one's fine. But this guy here is not in reduced echelon form because there's another non-zero entry in the column containing that pivot. All right, so this is not in reduced echelon form. All right, so what I want to do is just go through an example of putting a matrix in reduced row echelon form. All right, so here, where we used Gaussian elimination to talk about the process that leads us from a system to this matrix that allows us to use back substitution, that's called Gaussian elimination. This was getting a system to echelon form. Gauss-Jordan elimination is getting a system to reduced echelon form. Okay, so it's the exact same method. It just now the goal is slightly different, and we give it a new name. All right, so let's look at this. So the first thing I want to do is identify what the pivots are. This is already in echelon form because we have the pivots are here, bong, bong, and bong, and there are no zero rows, and each row contains more initial zeros than the one previous. So that is echelon form, but I want reduced echelon form, which means I want to make zeros there in there. All right. And so initially to do that, what I could do, I want to replace row 2 by basically, in order to get, let's see. All right, so I can piddle around with this. You don't have to keep these as the pivots, I guess, but we have to get it to the point where the pivots in those columns can only contain that 0 element. And so what I'm going to do is multiply the third row by 3 and add it to the second row and replace the second row by it. All right, so in other words here, multiply this by -3. So I'm going to kill this off. That's good, right? I want to get rid of that. So let's do that. If I do that, I'm not going to change anything with the first row. But if I do that to the second, I get 0, 0, 1, 0, -13, and 40. And I haven't done anything to the third row. Okay. But what I have managed to do, at least, is get zeros above that guy. Right. So we're good here. We're good here. We're not good there. Okay. So how do we get rid of that? Well, if I add R2 and R1 and replace R1 by it, right? So let's add R2 plus R1 and replace it R1 by that. All right. So now what does that do? If I add R2 to R1, I'm not changing the number of initial zeros, right? That still becomes 1 and -3. If I add those guys, I get a 0. That I get a 0. And if I add those two, I get -20. Add those two, I get 61. All right, and 0, 0, 1, 0, -13, and 40. 0, 0, 0, 1, 5, and -9. All right, so notice we have those are still, these are the pivots. So we haven't actually changed the pivots. Okay, I think I misspoke before. It was already an echelon form. And so reduced echelon form is an enhancement of that. It's not going to change where the pivots are. You just have to tinker around with the row operations to get the zeros in the right places. And so initially we wanted that guy to be 0 and that guy to be 0, and we've succeeded by just doing those 2 row operations. Okay. Now you can go through and solve it, right? So we have to, I'll set you up for this one, but we've gone through enough of the solutions to be able to safely do this. This guy here is a free variable, right? Once I know it, I'll put it up there, so there won't be another free variable from that guy. So x5 is free. We'll have x5, x4, and x3. When you plug all those up here, we still don't know x2. We have control over it, so that once we control it, we got x1. So there are 2 free variables, x1 and s2. We'll call x2 s1 and x5 s2. Okay. If I plug those in, notice here I have x4 plus 5x5 is equal to -9. Plug in the s2 and subtract to get -9 minus 5s2. So I have x4. Okay. If I plug those into the previous one, I have an x3 minus 13x5 is 40, but x5 was s2. Okay. And so if I add 13s2 to both sides, I get x3. I already have x2. Now plug everything in up here that we need. That would give me a x1 minus 3x2, which is s1, minus 20x5, but I have x5 as s2, is 61. And so if I add those to both sides, I get that. Right, and so again, you can write that using that ordered 5-tuple notation, but we have all of the values that we need. Okay, and then we have this theorem. Remember, echelon form is not unique, but reduced echelon form is. All right, so there is only one matrix that corresponds to a system that is in reduced echelon form that's equivalent to the first one. So this is unique reduced echelon form. So once you get it there, you don't have to worry. That's the only way you could possibly do it. All right. So what happened to my other page? Okay, and that's it. So again, at the comments on the other page are just applications. And so we'll look at some applications in class during our class discussion problems. But give this a go. Just get used to the matrix notation and using those row operations to solve systems, identifying free variables versus pivots, so on and so forth. So give the homework a go, and then we will meet in class. All right, take it easy.